Hi there folks, welcome to our review session for Calculus 2, the midterm coming up. We're going to be talking about integration techniques and some applications of integration tonight. So without further ado, I'm going to get started. Oh, before I do get started, actually, I should say there's a chat box over on the right hand side. If you have any questions at any point in time during these presentations of the problems, please ask away. That's what I'm here for mainly. And so if you have questions, ask them and I will try and answer them as best as I can. So without further ado, we're going to have a series of integrals. I'm going to go through quite a few and see if we can solve these things. So let's get started with this x squared sine of 3x dx. So if we didn't know how to approach it, let's think about the types of techniques that we have. We have integration by parts, and that's usually when you have a product of two functions and where we don't have one in terms of the other. Alongside that integration by parts, we have trigonometric integrals. Alongside those trig integrals, we have trigonometric substitution, and that's usually when we have a square root involved. We have partial fractions. And then from Calc 1, the thing that slips by people, we have U substitutions. Okay. So in this case, what are we actually going to use? Well, notice we do have a trig integral with this sine of 3x, but we have that x squared, and that is not a trig function. So most likely, and it doesn't seem like a u substitution because we have that 3x sitting right there. So we don't have the complete u substitution or trig integrals, or trig substitution. We don't have square roots involved. That's why we can toss out trig substitution. So that leaves partial fractions, which we don't have a fraction, so that's out. So what we're talking about most likely in terms of our integration techniques is integration by parts. Okay, so if that's the case, if we have integration by parts, what do? Well, we need a u and a dv, and if you recall, remember this thing will become an integral uv minus the integral v to u is what we're looking for, is how we're going to solve this thing. So we need u and we need dv, and that's, oh, I should say we are starting with the integral u dv. So what's u in this case? Well, we want to try and make things simpler for ourselves. So you could use sine of 3x, but if you put x squared over in this dv category, you're going to get an x cubed in the v. So that's just making it more complicated. So to try and make it easier, we'll choose u equal to x squared. That means du equals 2x dx. And then so our dv equals sine of 3x dx. And then hopefully we're starting to catch how to take this antiderivative. You would use u substitution in order to take the antiderivative. What will we actually have happen? Well, it should be negative cosine of 3x, but then we would need a 1/3 out here because of the chain rule, essentially, when we were trying to multiply the other way. Okay, so we have negative 1/3 cosine of 3x. And just in case if you don't understand that, please let me know. I'm happy to help out and show you all those steps in between. So when we take that integral, what do we get? We get this integral equals u times v, so that's x squared times the negative 1/3 cosine of 3x, and then minus v, so negative 1/3 cosine of 3x times du, which is 2x dx. Okay, so notice all that junk. So let's take this and move it down to here. We can brush it up just a little bit. So this whole thing equals negative 1/3 x squared cosine of 3x, and then minus minus, and then notice we have the 2 that can also go over here with this and pull that 1/3 out in front. So this becomes a plus 2/3 times the integral, and then we'll write the x in front just for simplicity's sake there, x cosine of 3x dx. And you might ask, well, how do we solve that integral? So, can't read what it says to the left of the UV. Okay, gotcha. I'll make that a little bit simpler for you to see. Thanks for asking, Chelsea. So we have u dv equals uv minus the integral of v du. Okay, does that look a little bit better? Can you see it now? That's just our integration by parts formula is all that I'm using there. So if not, just let me know and I'll write it a little bit larger. So now moving into this integral right here, the 2/3, we'll just multiply the 2/3 times everything. So this is another integration by parts. You can go through the same sort of categories and see which one fits. So you get u1 equals, once again we'll go with x, just because that makes it simpler. We get rid of the x now. We get down to dx for our du1. And then for dv1, the only reason I'm putting ones is because we called u and v something in the first case. So I'm just giving it a new notation. So if we have cosine of 3x dx, the antiderivative of that thing should be 1/3 sine of 3x. Okay, so now we can take this, we'll have negative 1/3 x squared cosine 3x. Now it's plus 2/3 times whatever's inside this integral. So I'll put a big parentheses for that integral. We go u1 v1, so we get x, and then that 1/3 sine of 3x minus, and now we'll take v1 du1, so minus the integral of 1/3 sine of 3x, and then we have a dx sitting right there. Okay, so moving that to the finishing touches here, we get equals, we'll have that negative 1/3 x squared cosine of 3x plus, we have 2/3 times 1/3, that makes 2/9. And then we'll have x sine of 3x. And then 2/3 times 1/3, that'll make a minus 2/9 times the integral of sine of 3x dx. But if you recall, I'll mark it right here, we had a dv equaling sine of 3x dx. We already got that integral. That antiderivative is negative 1/3 cosine 3x. So this thing equals negative 1/3 x squared cosine of 3x plus 2/9 x sine of 3x. And then notice we have negative 1/3 and you have a negative 2/9, so that makes positive 2/27. And then it'd be cosine of 3x, and now the one last thing that we need to remember is just put in that plus c. And we have our final answer right there. So that was integration by parts, and we used it twice. Just want to make sure we're all aware of how that works out and things like that. Any questions on that? If so, ask away, and I'm happy to kind of clear the air. Same thing with every problem. If you have a question right after I complete it, or during, just let me know, and I'll be happy to clear it up. So I don't see any questions at this point, so I'll move on. Okay, so now we have problem 2. All these are going to be solving integrals. I think we have 9 problems with just integration. So now what you might think on this one is you might initially think, okay, well, for this one, let's try u substitution. But you can try u equals natural log of x over x and things like that. No matter what you try, you're going to run into some headway. Just run into some problems. So I'm glad to hear the first one went well. That's awesome. So this one could be a bit trickier, though, just with the natural log of x and that x squared on the bottom. So you can make your list. Obviously, it's not going to be a trig integral, trig substitution. Those things are out because we have natural logs and x's, and there's no square roots or anything like that. Partial fractions, you might say, oh, maybe, but not quite, because you don't have a polynomial on top. So yeah, And I'm glad the bound would throw me here. I'm glad to see that. That's why I'm trying to address that. If we have a situation where we have a bound, how do we handle that? Well, what I recommend, if you're good with the antiderivatives themselves and not the bounds, there's an easy way to fix that. And what we'll do is, to kind of remedy that, I'll kind of show two methods along the way. So let's say we drop the bounds, and then we'll just plug them in once we calculate the antiderivative. Simple as that. So don't make it hard on yourself. You can just keep it easy and try and work it that way. So that's what we'll try and do. And so how do we do this? How do we actually solve for this one? Well, this can be rewritten as the antiderivative of 1 over x squared, or x to the negative 2, times natural log of x dx. And this might be a little bit easier for us to comprehend that it is another integration by parts. And in this case, we have u equal to the natural log of x. That means dv would be 1 over x squared dx. And in that case, remember that's x to the negative 2, so the antiderivative of that is negative 1 over x. And then that means the du, natural log of x, the derivative of that is 1 over x. Okay? And you might not get this at first, and that's fine. If you're struggling and say you tried u substitution and things like that, try and guess, see if you can work the problem. If you don't, just regroup, try it again. And same thing over and over again. It's going to happen. The more practice you get, the more you start to see, oh, this one's integration by parts, this one's u substitution. Those are the real tricky parts. Hopefully, though, you can see you can eliminate trig integrals, trig substitutions right away. Okay, so that means that this antiderivative becomes, and I'll show you how, if you were to do this up top, right, how we could write that as well. So this one goes, oops, I don't need the integration part just yet. It goes u times v, so we go natural log of x times negative 1 over x minus v du. So we get negative 1 over x, and then we have times another 1 over x, and then we have a dx. Okay. So now if you had evaluated this, the way to write this, we just put the bounds in at certain places. So I'm going to write it a little bit nicer though. We get negative natural log of x over x, evaluate at 1 and e, which we'll plug those in on the next step. And then minus, oh, notice we have minus and minus, so I'll put plus the integral from 1 to e of 1 over x squared dx. Okay, so we're in pretty good shape at that point. So we have a couple different routes, and I'll kind of explain where to go from here. So as we mentioned, this is negative natural log of x over x. Okay. And so where do we get our next bit? So we'll get plus 1 over x squared. So if this is plus the integral of 1 over x squared, we already evaluated that integral, and so that means it's just minus 1 over x. And then for this part though, with an antiderivative in general, we put a plus c. So in terms of our original formula though, here's what we get. We can have the negative natural log of x all over x, and I'll put the 1 over e at the very end this time. So then we get minus 1 over x evaluated at 1 and e. Okay, so keeping all that in mind, let's write in blue. How do we get our final answer? Well, plugging in the bounds is actually the easy part. It might not seem like it at first, but it's not too bad. So you get negative natural log of e over e minus 1 over e. Then we got to subtract off. Now we plug in 1. You get negative natural log of 1 over 1 minus 1 over 1. Okay. So, by the way, this thing right here, that is just 0 because natural log of 1 equals 0. Natural log of e over e. So we have, that's negative 1 over e. Because natural log of e, that's a log base e of e to the first, so that just becomes 1 up top. So you have negative 1 over e minus 1 over e. So, and then notice you have a minus and a minus. So this part, if you combine these two terms, you'll get 2 over e. So negative 2 over e and then minus and minus makes plus 1. Or another way for us to have written this is equal to 1 minus 2 over e. Okay, and that would be a good final answer. Even before that would have been a fine final answer. So, any questions on that one? I know it gets kind of scary when you have bounds there, but as I said, just take your normal antiderivative and then go back and plug in the bounds. Don't let the bounds scare you. It's fine to do all your work and then plug it in afterwards. Just make sure you aren't putting bounds down when you're taking that general antiderivative. If you are putting the bounds in, you're going to do something similar to what you saw right at that underlined part. So hopefully that makes sense on that. And we'll keep on chugging along unless any questions pop up. So, oh, okay. So yeah, the E being intimidating. Yeah, the nice part with that. So the question was about, or comment was about the E being intimidating. Yeah, if you have a log base E of x, that's the same thing as the natural log of x, right? So if you have the natural log of e to say some 512, what that's going to equal is 512. It's just what's up in the exponent. So it makes your life a lot easier. And then anytime you have a log base b, regardless of what that logarithm is, if you have a log base b of 1, that will always equal 0. So those are the two components that were used there. Don't let them scare you off, right? It seems intimidating because there's e's and natural logs, but really, if you start to grasp that logarithm, it'll make things a lot easier. So, all right. Now, in terms of this one, we have cosine to the 4th theta d theta. So this seems to be, there was a few routes, integration by parts, partial fractions is out, obviously. Then we have trig integrals, and we have trig substitution, and then u substitution. Well, notice if we tried u substitution, you'd have u equal cosine theta, but then you'd have du equal sine of theta d theta. So that one's out in terms of no u substitution. So now you're down to trig integrals and trig substitution. But remember, trig substitution deals with the square roots and all that stuff. We're trying to handle roots in those cases. And so that's out. So basically this is a trig integral. Now we just have to remember, okay, how do we handle the case where we have cosine to the 4th theta? Well, there's a series of trig identities, and the big 2 when you have an even exponent up there. Now sometimes if it was cosine cubed, that becomes a different problem. But you need to remember sine squared theta is 1/2 1 minus cosine of 2 theta, and then cosine squared theta equals 1/2 1 plus cosine of 2 theta. So that means that this integral, using that second identity, we can write this as, well, first off, let me write it as cosine squared theta squared d theta. Then what happens? Well, you can write that cosine squared theta as 1/2 1 plus, so 1/2 1 plus cosine of 2 theta. And then we're going to square all that junk, d theta. Okay. So moving forward from there, where do we go? Well, we get 1/4 times, now we just need to basically square that whole thing, so we get 1 plus, well, you'll get 2 times that product of those two things, so you get 2 cosine of 2 theta plus cosine squared of 2 theta. So that looks like a uh-oh moment, but it won't be too bad. And d theta. So we can pull that 1/4 out, and then, oops, one integral there. We'll have 1 plus 2 cosine 2 theta. Now here's the next trick. Cosine squared 2 theta. So what that means, if we have cosine squared of 2 theta, we can rewrite this thing. And how do we rewrite this thing? Well, we take 1/2, and then we'll go 1 plus cosine. Well, notice it was theta here, and it became 2 theta, so it goes 2 times 2 theta, right? So that will be just 4 theta. So this thing becomes plus 1/2 1 plus cosine of 4 theta. And then we'll write our, close off our parentheses and put d theta. So this part's just 1/2. We can take that right there. And so that would make 3/2. So it equals 1/4 times 3/2 plus 2 cosine of 2 theta plus, and then there'll be 1/2 cosine of 4 theta. And we take all that and go d theta. So now we're going to use u substitution along the way if you don't remember it, but just let me know if I go too fast here. I'm happy to slow down those pieces in between. So the first part is going to be 3/2. Well, what's the antiderivative of a constant? Is this 3/2 times whatever the variable is. So we have the 3/2 theta. The antiderivative, so I'll put the 2, that's just a constant, so we won't worry about that. The antiderivative of cosine 2 theta, so first off it's going to have a sign involved, and it's a positive sign. So we'll have sine of 2 theta, but notice we want the derivative to become cosine of 2 theta, so we'll have a 1/2. Alright, basically you take the reciprocal of the constant in front of that coefficient there. So we're good on that part. Plus now 1/2, same rule applies here. We'll have sine of 4 theta, but now we'll need a 1/4 out here. Okay, and then we add this constant c. And oh, let's close that all off. Okay, so if you wanted to, not necessary whatsoever, this is totally fine, but we could do 1/4 times 3/2, so what is that? That's going to be 3/8 theta. And then plus, notice the 2 and 1/2 cancel in this next one, and so we're left with 1/4 sine of 2 theta. And then to finish off we have plus 1/32 sine of 4 theta plus some constant c. Any questions on that? So that's a good old-fashioned trig integral. Let's take a look at our next one. We have our tangent cubed natural log of t divided by t. My question for you is, what do you think we'll use in this one? What sort of techniques will we use to try and tackle this integral? Let me know, and it's alright to take a guess. Let's see what happens. So yeah, trig sub's a good guess, but remember, trig substitution, that's a real good guess, but we usually want things like square root of a squared minus x squared, or square root of x squared minus a squared, or square root of x squared plus a squared for the trig subs. Okay? So u substitution, yes, that's correct. In Chelsea, for the u substitution part, you got that correct. So you can get extra credit. Just shoot me an email reminding me for the u sub. That's a first step. Now, what would you call the u substitution? So I see that you agree there, Dimitri. Good job. What would we call our u substitution? That's a great first step here. So that means u equals something, and then du equals something else. So if we take a look, the u substitution that we're actually looking for in this case would be u equals natural log of t. Okay, and so yeah, the tan cubed divided by t, that's close. It's actually that natural log of t, and the reason why is because we get du equals 1 over t dt. So notice we actually get that other piece for free, right? Yeah, and that's it. That's exactly it. So if you tried tan cubed of something like 1 over t, you try it out, and notice if I try tan cubed of say 1 over t, right? What does du happen to be? Well, if I do my derivative correctly, I get 3 tan squared 1 over t times negative 1 over t squared, right? And so you can recognize pretty quickly, oh wait, this isn't matching what we have up here. So yeah, and so as soon as, and that's exactly right, the u equals 1 over t, that's a pretty good guess too. The du, meaning du, that's right, the du equaling 1 over t, that's the big part. And you saw, if we take a guess that's incorrect, we just start over. That's all. It just takes a second to regroup. So now that we have this, we can rewrite this thing. So this becomes the integral of tan cubed of u, and just in case you didn't see that 1 over t dt is du, here's an easier way to do it. You can write dt equals t du. So notice we have t here, and then dt equals t du. And if you've done things correctly, notice the t's cancel, and you're left with the integral tan cubed u and then a du. Simple as that. So this looks a lot better than what we had before, hopefully. And now hopefully you can see this becomes, so there is the trig part, it's actually a trig integral. And the trig part that you're going to use, so sometimes you use things like sine squared plus cosine squared, sine squared theta plus cosine squared theta equals 1. In this case, the trig substitution, so first off, you might remember that tangent squared theta plus 1 equals secant squared theta. Okay, so what that means is that tan squared theta equals secant squared theta minus 1. If you don't remember that formula, let me know and I can show you where it comes from. It just comes from that sum of the sine squared theta plus cosine squared theta. So you can rewrite this integral, first off, as tan squared u times tangent of u, and then we have a du. And don't forget about that du just yet either. We're going to use that a little, or the u a little bit later after we evaluate this integral. So we can rewrite this as secant squared u minus 1 times tangent u, and then we have a du. And what I'd recommend in this case is probably breaking it up into two different integrals. So the first integral will go tan u secant squared u du. And then in the second case, minus the integral of tangent of u du. So now, any guesses on that first one? What are we looking at for our antiderivative? So how will we calculate this antiderivative? Any ideas? I'm interested to hear what you all think on that one. And the same thing with the second one. How would we calculate that antiderivative? So it takes a little bit of practice to catch these, but what sort of techniques are we using now to finish this thing off? So yeah, we want to go back to that trig substitution. That's close. Remember, trig substitutions, we need square roots involved, right? So you have square root of a squared minus x squared, or square root of x squared minus a squared, or square root of x squared plus a squared, right? There is no square roots in this? Yeah. Okay, so not what you meant? Yeah, that's good. But yeah, the trig subs, we're always looking back at that for the square root stuff. So if you see square root, that's when we start thinking trig substitutions, or at least x squared plus some other constant squared, like in the denominator, even if it isn't of that form. Basically, the idea of trig substitution, just an FYI, you're trying to use kind of like an inverse trig function, and that's a way to kind of do it. That's what's the methodology behind all that. So if it's not a trig sub, I agree there's something, you got one of those words correct. So either it's a trig integral or u substitution. So which one is it? And there's no reason to apologize either. I'm hoping to see some guesses and just want to see what you all are thinking along the way. So yeah, a u sub would be the trick. Now, except we already use u, so you see u star, that works just as well. So we can use u star. And then in this case, what do we want u star to be? Well, yeah, we'll go tangent of u. And then that means du star in this first case equals secant squared of u du. And so don't get confused with those different symbols. I'll use in the other one, any ideas for the tangent of u? So I can rewrite this first part in the meantime. So we'll rewrite this integral as just, well, notice this is just u star du star minus, now you might want to write, this one's tricky because it tends to trip up a lot of people. That tangent of u, there might be another way you want to write that. Any ideas there? So instead of the tangent of u, I'm actually going to erase this real quick and write it in a slightly different format. And hopefully that'll make sense. Tangent, remember, is just sine of u divided by cosine of u. Right? So don't get lost in terms of where that tangent went. It's still there. We just wrote it slightly differently. And then in this case, this is also a substitution, like a u sub, I sub, or whatever you want to call it. I'm going to use w here. If you go w equals cosine of u, that means dw equals negative sine of u du. And so if you wanted to make it so it works out perfectly, you get negative dw equals sine of u du. So notice we had that u star du star minus, now it should be an integral of negative dw over w. And so both of these things we can finally integrate. So you get a u star squared, and then we'll have a 1/2 out in front just by that reverse of the power rule. And in the second case, minus and minus makes plus. And so we'll get plus, and then dw over w makes natural log of the absolute value of w. So moving forward from there, though, what does that equal? Well, this is the same thing. 1/2 u star squared. We know u star is tangent u, so 1/2 tangent squared of u. Well, I need to toss a plus c at the end of that. And in our second case, we get plus the natural log of w. What's w? Well, it's cosine of u. And then plus some constant c. And so now we're ready to go back and plug in the u value that we started with, and I'll put a little marking up there. So this is 1/2 tangent squared of natural log of t, and then plus natural log of cosine of natural log of t. So you have natural logs inside of natural logs, and then plus some constant c. And that is our final answer there. Questions on that? I know that was a tricky one because it involved u substitutions pretty heavily along with the trig integrals. Just want you to see some of that stuff, how it works. Okay, don't see any questions thus far, and so I'll keep on moving. Alright, so now we have this integral of x squared over the square root of 9 minus x squared. How will we approach this one? So notice we have that square root involved. Yeah, so a comment on the last one, recognizing you need to break it apart is a tricky step, and I'll kind of mention that one more time. The real reason why, if we set, say, u star equal to tangent u, notice that piece, that 1 right there, we aren't going to be able to work with it so much, right? So we'll get the du would work for the secant square, but we have that negative 1 right there, and we can't fix that. So breaking it into that extra u substitution, that is the big thing that we need to work with over and over again. So yeah, great comment there in terms of we do need to break these things apart. That it is the tricky